for the introduction. Ladies and gentlemen, I want to welcome you to the presentation of my co-author, Mr. Sander, and me about cracking behavior under the influence of different elastic plastic material models. As part of my studies, I analyzed crack growth in power plant components. First investigations were made already using linear elastic fracture mechanics. But to enter these results, it is necessary to do also elastic plastic simulations. In that case, there are examinations of the influence of ratcheting in the crack tip by, for example, Tom et al. These examinations have shown that ratcheting is important for crack growth, and because mechanisms in power plant components are stress controlled, it is necessary to find a material model that describes ratcheting behavior correctly. The material models I investigated are the Chavoche model and the Eurovan model. In the following, I want to show you some results about the description of material behavior. And moreover, I did some elemental examinations of cracking behavior depending on the material model, for which I want to give you a short conclusion and an outlook. To describe material behavior, it is necessary to know the right model parameters. Therefore, the identification is based on stress-strain curves from uniaxial cyclic experiments for the shown material. The strain amplitude is 1.2%, and today I want to show you the results for an example temperature of 400 degrees Celsius. The first model for which I had to determine the parameters is the Chavoche model. Its parameter identification was made according to Hassan et al. And as suggested, 3 backstresses were used, where the parameter C3 is the slope of back curve part. The parameters C1 and 2 and gamma 1 and gamma 2 were determined by solving these equations as an optimization problem, which leads to dependence of the identified parameters on, for example, of course, the starting points, but also on the yield stress as a model parameter. The usage of a yield stress of 100 megapascal leads to the best parameter set, which is listed in this table. Here on the right-hand side, you can see that this analytical result fits the experimental data well. Next to the kinematic parameters of the Chavoche model, I identified isotropic parameters. Therefore, I used this equation and the maximum stress over the accumulative plastic strain. In this table, you can see the results of this identification. The parameter determination of the Eurovan model was much easier. It was made according to Düring for 5 backstresses, and the first step was to select 6 sampling points from experimental data, considering Mesing behavior. In the next step, it was quite simple to determine the parameters analytically from the slopes between the sampling points, which leads to these parameters. To validate them, strain control simulations were made in Abacus on a plain rectangular model, and for the Eurovan model, a yield stress of 250 megapascal was chosen or applied. As you can see, both material models are able to describe stress-strain behavior under strain-controlled loading very well, and to determine the ratcheting parameters gamma 3 and kappa repetitively, stress-controlled simulations were also made. Here you can see some the variety of the results, and they show that the usage of the Chavoche model leads to an overestimation of ratcheting behavior, which is an opposite to the better possibility to describe ratcheting behavior under the usage of the Eurovan model. Next to the ratcheting parameters, there is an influence of the development type. That means the usage of plain stress elements leads to a better description of ratcheting behavior than under the usage of plain strain elements. I did not only use kinematic hardening parameters in the Chabosh model, I also combined it with isotropic parameters. And as you can see, the combination of both leads to a better description of the maximum stress over the number of cycles than only using kinematic hardening parameters. There's also an influence of the isotropic parameters on ratcheting behavior. You can see there's a parabolic curve of the strain maximum over the number of cycles, which is an opposite to all the other simulations where the curve is nearly linear. After finishing all the parameter identification, I analyzed cracking behavior depending on the material model. Therefore, two and three-dimensional cracked models with a width of 8 mm and a height of 12.5 mm were simulated. The loading was a tensile stress of 100 MPa and the crack depth was 3 mm. To determine the J integral, 5 contours around the crack tip with an element size of 0.02 mm were applied. The first model I analyzed was a plain rectangular model, and here you can see the results of the J integral over the number of contours. As you can see, the usage of the Chabosh model leads to higher values for the J integral than under the usage of the Numerical model, which results from the overestimation of ratcheting behavior. And moreover, the Chabosh model shows a better convergence behavior, especially under the usage of a quadratic approach. After plane simulations, three-dimensional models were analyzed or simulated. The first one was a cuboid with a straight through crack next to some kind of semi-elliptical crack with an A to C ratio of 0.75. Interesting points of this crack front are the point A and the point B. Other three-dimensional models I analyzed were a pipe under tensile loading with a circumferential crack and a hollow sphere under inner pressure with also a circumferential crack and a semi-elliptical crack front. For all the models, the advantage of symmetry was taken. In this table you can see the deviations of the J integral between both material models, where the base value is the J integral of the Numerical model. Most of the deviations are about 20%, which means that the J integral of the Chabosh model is about 20% higher than the J integral of the Numerical model. As you can see, there are also some deviations between the points A and B, but the most eye-catching deviation is this one. The usage of plane stress elements in two-dimensional simulations may lead to a J integral under the usage of the Chabosh model is twice as much than the usage under the usage of the Numerical model. It underlines the different influence of the element type between both material models. All in all, we have seen that the Chabosh and the Numerical model lead to good strain-controlled numerical mappings of experimental data, but the Numerical model describes the ratcheting behavior better. From the crack simulations, we have learned that there are higher values and better convergence behavior of J integral under the usage of the Chabosh model, and the deviations of J integral between both material models of about 20% are present for two- and three-dimensional models. In the future, I want to realize expressive results under the usage of the Chabosh model because its computational time is a lot shorter than under the usage of the Numerical model. Moreover, I want to applicate the results on elastic plastic crack growth simulations, on power plant components under transient thermal loading, and because of that it is necessary to use temperature-dependent material parameters, and this option is already implemented in Abacus for the Chabosh model. Last but not least, I want to thank the Ministry for Economic Affairs and Energy and our project partners, and of course I want to thank you for your attention.